Hi, this is Dr. Marshall, and this is the first lecture in the 1-5 problem solving section of the first physics unit. I think it'll probably take 3 or 4 lectures to finish this, but we should be able to finish it in one part without dividing it up into more than one part. Okay, so if you the whole purpose of this section of the discussion is to create a strategy, a consistent strategy for you to use to figure out how to learn to solve um, motion problems. In order for you to visualize problems more clearly and make certain that you don't forget anything important, you have to have some kind of a strategy. And you have to perform the strategy consistently and faithfully every time, or because of the amount of information that's in the word problem that's not stated directly, it's just implied, you will forget things. And so the strategy involves using a motion diagram to collect this information, then writing this down so that we can see it in a list form, and that will help us to be able to figure out what formula to use, and then we perform the solution. So your target will be, I will be able to describe and use a strategy involving the creation of motion diagrams and a standard set of motion equations to solve any basic motion problem in one dimension. Okay, that's our goal. And again, the reason that you want to do this is because there's so much information in a lot of these problems that's just implied and it's not really stated. And unless you have this pattern of activity that collects all of this information, then it's going to be difficult for you to be successful here. So we've got this standardized approach to solving motion problems that we need. Without it, we'll say that important information will be missed. And then the how of this, in other words, how will you show me that you know this? You will correctly employ a standardized strategy in solving basic motion problems 80% of the time. Okay, so what is this strategy? Well, we've already talked about the idea that it involves using a motion diagram, and the motion diagram it's got two main purposes, and the really big purpose for our situation is that it's going to collect all of the information for us. We're going to use it to collect all the information in a very standardized way and show that information visually. The second purpose is to show it visually so that we can see in our mind's eye, or picture in our mind's eye, what's going to happen. Okay, so the first part of this is drawing an appropriate motion diagram. And in order to have an appropriate motion diagram, I need a frame of reference. And this is going to represent my frame of reference, our frame of reference. It's going to tell me where the origin starts, and then it's going to tell me the direction of positive x values. So the first thing we need to do in in our collection process is collect the initial piece of information. Where do I start at? Where is my initial position? And we symbolize that with x0. And most of the time, we'll be able to define whatever we want as that starting position. The problem won't tell us. But be careful, because sometimes it will say that the motion begins so many meters east or north of the origin, for example. Okay, but it oftentimes, most often, will allow us to say our initial position in our problem is going to be 0. Okay, then we need to identify the final position and place that on the axis. And it may be that we don't know what the final position is. It may be that we want to find the final position with our activities. Okay. Third piece of information, we're going to identify the initial velocity. Okay, and also be aware that just because something doesn't have a piece of information associated with it doesn't mean that it's not important. It means that we need to go find it in some way. Okay, so for example, our point of the problem is to find this displacement here, but there may be other things that we need to find that aren't the direct answer. So the initial velocity here is 0 meters per second, and we're going to put the second position, or the final position, or the final velocity further to the right. Okay, so identify the final velocity and place it on the axis. If constant velocity, just place that velocity on the axis. But we're going to place an increasing velocity here on the x-axis. So drawing velocity vectors to also illustrate decreasing or increasing or constant velocity. Okay, this is going to tell us what the motion of our object is doing. Okay, so the next thing, we need to identify acceleration and place this on the list. Okay, so we've got the initial and final velocities here. Okay, we've got the initial and final velocities here, and we've got the vectors that are drawn in indicating how fast the ending of this is compared to the beginning of this, where I'm not moving at all. So we're going to place the acceleration value on the x-axis as 3.6 meters per second squared. Let's just say that that's what this is in this case. And so I've got all of my information collected. I also need to put in a vector for my velocity here. I forgot that. So we're going to put the vector in for that. And remember that the vector goes in the direction of increasing velocity arrows. And so my velocity arrows are getting bigger if I'm going to the right. So I'm also accelerating to the right. Okay, so if the velocity or the acceleration is 0, we can use a dot here like this instead of a vector arrow. So if I don't have an acceleration, but I need to record that on my position time or my motion diagram, then I can use a dot to indicate that. If values are unknown, we're either going to use a question mark like we did here, or I might actually know a formula to find that value from some other means, and I could put that on the motion diagram and help me find that value as well, right on the motion diagram. In any case, we won't use that approach for a few weeks yet. Okay, so once I have all this information collected, okay, again, initial position, final position, initial velocity, final velocity, acceleration, and then time, I've got to place all of this in my given list. Okay, I've got to write this down so that I can look at it visually to see what I've got to compare to the formulas that I'm going to use. Okay, and I'm going to write it down in the same way. Initial position, final position, initial velocity, final velocity, acceleration. Okay, then we're going to place the information that we need in a need list, and in this case I'm saying I want to find out how far they went. What was the final position given this set of circumstances? So I need X. Okay, and now we've got all of the formulas to consider. And one of the most common things that individuals constantly tell me, I don't know which formula to use. I don't know which formula to use. If you follow this set of reasoning, you'll be able to pick your formula every single time. Okay? I want your strategy to be a strategy that is foolproof and leads you to the correct solution every time. So we're going to start with, there's some questions you can ask yourself in order to select the right formula without having to know in advance what formula to use. Okay, so in addition to the two basic motion formulas for velocity and acceleration, we've created a list of 5 additional formulas created from these two formulas, the velocity and the acceleration formula. Okay, and these formulas are designed to use under specific circumstances. So let's ask ourselves questions about those circumstances in a standard way, and that will lead us to decide which formula to use. Okay, we call these the Big Five. We can ask a series of logical questions to help us narrow down which formula to use. The first question I will always ask, and it's going through my mind even as I'm reading the problem, have I been given time or do I need to find time? And if the answer is no, there's only one formula that you can use. You have to use this formula. Okay? So if you ask yourself the question, do I have time or do I need time? And the answer is no, you already know what formula to use. It has to be this one. And in our list, that's the last formula, so I'll oftentimes call it the last formula. It's also the one students don't want to use very often because it's got squares in it. Okay? Nevertheless, you have to use this. V squared equals V0 squared plus 2a times x minus x0. Okay? So you would write that formula down in the formula list. Okay? If you cannot use this formula, in other words, if you have time or you need time, then ask, do I have constant velocity or do I have an acceleration? And remember, in physics, an acceleration just means a change of velocity. So I only have two choices. Do I have a constant velocity or do I not have a constant velocity? And if the answer is you have a constant velocity, then you have to use the first equation that we write down, x equals x0 plus velocity times time, because it's the only equation that describes motion with a constant velocity. None of the other 5 equations describe motion with a constant velocity. Okay, only this formula does. So if you have an acceleration, and in this case you do have an acceleration, we don't have time, so we're going to end up needing to use that formula. This case we do have an acceleration, so I wouldn't have been able to use this. Okay, so if I can't use this, then I go to my next step. If you can't use this formula, ask, do I have a final velocity? And if the answer is no, out of the 3 formulas that you have left, the only one that doesn't require a final velocity is x equals x0 plus v0 times time plus 1/2 at squared. It does require that you have an acceleration and a time, or one of these other variables. But if you do not have a final velocity and you've gotten this far, you have to use this formula. Okay? If you do have a final velocity, the last question to ask is, do I need to use or find initial or final position? If you don't need to use or find final position, the easiest formula to use is v equals v0 plus acceleration times time. On the other hand, if you do need to use or find final position and you have an initial and a final velocity, you have to use this formula. Okay, so if you follow this practice religiously, I promise you, every time you approach a problem, this will vastly improve your skills, and it will become less and less difficult to find the correct formula. You will soon not be saying, I just don't know how to find the correct formula. Now, although this will not happen initially, eventually, even if you do find the right formula, you're going to find that you may not have all of the information that you need to use that formula, and you'll have to take another approach to find that information. This will be in the future. Once you select the formula, inspecting to see if you have all the information will alert you to this problem. So if I've said I need to use this formula, and then, oh, wait a minute, I don't have the final velocity like I thought I did, then maybe I have to go find the final velocity some other way before I can use this formula. Okay, but we'll see how to deal with this when we start to learn about forces, because that's the circumstance where this is going to come up. Okay, so let's stop this video right here so that we don't run into the 15-minute problem, and then go to the next video.